times 10 to the power minus 6 meter cube. Okay. So from here, your shear stress at point C is equal to V over I. Q is 22.5. So rule number 1, right? V over I are always constant. Okay. Thickness is 0.01. Q itself is alone 1, so this is okay. So this is 22.5 power minus 6 divided by 0.01. So it's 2.25 times 10 to the power minus 3. And this is V over I. Okay. So that is shear stress at point C. Then we're going to find the shear stress at point B. Right. Still the same. Okay, we're going to apply thin wall, wide flange, analysis. Right.
So Eugene, it would be wrong to apply thick wall in this section here that we're talking about?
Yeah, because if you apply thick wall, you have to take the left and right structure.
Oh, I see.
Does that make sense? Right? If you take thick wall, all right. So if you take thick wall, right, you have to take this entire.
And then we would have to double our previous section as well if we were to do it that way, and it'd just be much more confusing.
Forget it. Don't think about it.
Okay.
Okay. Don't think. I know the answer will be the same. I'm aware that the answer will be the same, but don't think about it. Because why don't think about it? Because then the purpose of thick wall and thin wall, what are the difference, is non-existent. You get what I mean?
Okay.
And then if you want to change the rules, the problem with the rules that I've derived down here, okay, the 5 rules I've derived down here, you cannot deviate. Okay, if you deviate, this might not work because I've not tried before if I deviate. Okay, that's the problem.
Okay, makes sense.
Then thin wall analysis. Okay, so the Q is still Q. The thickness now changed to 0.02 meters. Okay. Okay. So the Q at B is equal to the Q at point C plus by the width 20, the depth 50, the centroid 80 minus 50 divided by 2. Okay. So this will be equal to 22.5 times 10 to the power minus 3 plus by 80 minus 25 times 50 times 20 is equal to 55. Oh, positive. Okay, sorry. 55 times 10 to the power 3. So this is equal to 22.5 plus by 55. So 37.5 times 10 to the power 3 millimeter cube, or 77.5 times 10 to the power minus 6 meter cube. Okay. Then the same thing, the shear stress at point B is equal to V over I. Q is equal to 77.5 times 10 to the power minus 6. Now the thickness changes to 0.02. Okay. 77.5 power minus 6 divided by 0.02 is equal to 3.875 times 10 to the power minus 3. V over I. Okay. So what we realized that if we compare VC, hey, there you go. And stress at point B, shear stress at point B is higher now, right? But we cannot say the centroid is the highest because now the centroid or at point A, the width is bigger now, right? Okay, so now this is where the difference now. So I want you all to now focus on thick wall analysis. Okay, so now we want to find the shear stress at point A, and we're going to apply thick wall analysis. Right, and the thickness now there's no more Q. Okay, thick wall, there's no more 1Q or 2Q. Okay, is there a way to set the counter to show only? Yeah, there is. And the button, if you look at your calculator, the button is known as the ENG button. If you press the ENG button, it will give you the 10 to the power 3, 10 to the power 6. Okay, can you try that, please? Okay, so now the thickness is now equal to 0.12 meters. Okay, 0.12 meters. So 0.12 meter. Okay, so we know, right? So the area we have to so I'll divide up the area what we have. Okay, so we know this area. We also know this area, right? And then when we find point B, we know this area, right? So everything you have to divide by 2, multiply by 2. The only thing that we don't know is this. Okay, the only thing that we don't know is this. Okay, so we find the Q at A. So for this case, you can directly do twice, multiply by 77.5 times 10 to the power 3. Right? So these are for the thin wall region. Okay, plus the width is 120. Now it's the thick wall region. Okay, the depth is 30, and this will be 30 divided by 2. Okay, so these are the thin wall region. The 2 because of left and right. And over here, this is our thick wall region. Okay, that is our thick wall region. So from here, this will be equal to 120 times 30 times by 120 times 30 times 30 divided by 2 plus by 77.5 power 3 times 2 is equal to 209 times 10 to the power 3. Or 209. Okay. So now we find that the shear stress at point A is equal to V over I. Now the first moment of area seems to be the biggest, but the thickness is also the biggest, right? So now when you put this is 209 power minus 6 divided by 0.12 is equal to 1.741. Wait, 209 minus 6, Eugene, come on. Yeah, 209 power minus 6 divided by 0.12 is 1.741 or 1.742 times by 10 to the power minus 3 V over I. Okay, so we're going to compare now. Okay, so we're going to compare now. So the shear stress I'm almost done, okay? We can go for a break in less than 5 minutes. So shear stress at point A is equal to 1.742 times 10 to the power minus 3 V over I. The shear stress at point B is equal to what? Point B is equal to 3.875 times 10 to the power minus 3 V over I. And then the shear stress at point C is equal to 2.25. So of these three numbers, we know that stress at point B is equal to your tau max, right? It has the largest coefficient, right? So from here, we know that tau max is equal to 3.875 times 10 to the power minus 3 V over I, and this will be equal to 75 times 10 to the power 6. So we found our V over I, okay, the V over I is equal to 75 power 6 divided by 3.875 power minus 3. It's equal to 19.355. Okay, times 10 to the power 9. So therefore, the shear stress at point C is equal to 2.25 times 10 to the power minus 3, right? Multiplied by what? Multiplied by 19.355 times 10 to the power 9. I know I'm squeezing, my bad. Okay, so 2.25 power minus 3 by 355 power 9. 43.548 or 549 megapascal. Okay. And then the shear stress at point A, 1.742 10 to the power minus 3 multiplied by 19.355 times 10 to the power 9. Okay, so this will be equal to, let me shift this over. So 1.742 power minus 3, 19.355 power 9. It's got 33.716 megapascal. Okay, so that is all for thin wall analysis. Okay, when we come back, we are going to do a different type of analysis to find the spacing of your nails, or the spacing of your nails, okay, so that it can withstand or you can calculate the shear stress required for the nails. Okay, we will come back at 10:45. Okay, I'm going to stop recording now.